So let's start reviewing on what we did last time. And what you're seeing here is that we started off with the work energy theorem. And as we looked at the work energy theorem, we said here is that when an external force, F of external, does work on a system, something about the system changes. That something is what we call, maybe I should have put this in quotes here. This something is what we call energy. And so the work energy theorem says that if I have a constant force, and remember, most of these forces are not constant, they're actually dependent on position. And as a result of this, what ends up happening is that you would have to do some type of mathematical calculation called a line integral. And when you do this line integral, you would find that you go through some mathematical process here. Now, but it turns out that that's not our goal here in this chapter here. What our goal is really to pay attention to how do we use these things. And the way we use it is that we have three situations where the change in energy could be positive, negative, or zero. So if I talk about positive work, that means here that the external force and the displacement point in the same direction. So if they point in the same direction, we call that positive work. So a conceptual way of looking at this is that the energy, which we've been calling stored work, flows into the system. It flows into a low energy system and it excites the total energy of the system. It brings it to a higher energy state. So work is this transitional thing. It takes energy from a low to a high energy state. And so when we look at this thing, this energy E1 is actually meaningless. This energy, E2, this has no meaning at all. It is meaningless. So when somebody says, I'm low in energy, that is a meaningless statement. And when I look at energy E1, that is also meaningless. The only thing that's meaningful is what's given by the work energy theorem. And so it's this change in energy that's meaningful. And so you can see here is that there's a direct, that when we look at what we mean by energy, it's this work that now gets stored as stored work, which is what we call energy. So therefore, positive work increases the energy of the system as being stored work. In everyday language, we start to say there's a flow of energy into the system. In a very analogous way, we could say the same thing with negative work. Negative work is when the force and the displacement are in opposite directions. So this combination gives you a negative quantity. So physically, what we're seeing here is that when negative work is done, we are taking some of this stored work or energy and we're pulling it out of the system. In other words, the system goes from a high energy state to a lower energy state. Again, this working process is a transitional thing that changes the energy of the system. So once again, this energy, E2, this energy, E1, is meaningless. The only thing that's meaningful is this change in energy. That's the only thing that has any physical reality. So negative work decreases the available energy of the system. And in our language, we say that there's a flow of energy out of the system, therefore reducing the system. But the situations that we typically deal with, believe it or not, is zero work. Now, when I look at zero work, there's a couple of ways that we want to think about it. One possibility is that zero work occurs when the external force and the displacement are perpendicular to each other. In other words, there's a 90-degree angle between these two vectors here. That turns out to be zero work. So perpendicular forces will never change the energy of the system. And roughly is because there's no displacement. And we'll talk about this a little bit more in a moment. But the way we typically use energy is that if there is zero work, then the exact amount of energy flowing into the system and out of the system occurs. That's the big difference right here. So what this is telling me here, that the amount of coming in plus the amount of going out, that equals zero. And because that equals zero, the change in the energy of the system is zero. That means that there's no energy change. So in this case, you see that in the other ones, I went from violet to orange. I tried to show you that the system changed in some way. Here, I'm going from violet to violet, showing you that the system is exactly the same. So when I look at it from the work energy theorem, then if there's no change in in energy, then this means here that the net work also has to be zero. So in this case, the work coming in versus the work being pulled out, those balance each other and you get zero work. Therefore, the energy of the system does not change. So now what we want to do here is that we want to apply this. Okay? We want to apply this thinking to a simple system. And here I'm going to talk about a block. And what we're going to do with this here is that we're going to drag a block across a surface with friction. Now, the language here is tricky. Okay, there is really, how do I say that? I don't know how to put this in good language. But this is what we say here. According to the work energy system or energy theorem, we know that the net work has to equal the change in energy. So what I'm going to do here is that I'm going to sort of make up language. And here's what we know. So if I have a network, if this network is zero, then I'm going to say that the system is in equilibrium. However, you know what? I shouldn't have written it like that. Maybe what I should have done is I should have said it equals. But if it does not equal 0, then I'm going to say that the system is in a non-equilibrium state. So these have very specific meanings. This tells me that the energy of the system before and afterwards are exactly the same. In this situation, they tell me that these two energies are not the same.